Hi, this is Mr. Phillips, and I'd like to have a quick discussion with you about free body diagrams. But first, let's do a short review of what we already know. So here we have a picture of me holding a tennis ball in my hand, and the components in this system would be the hand, the ball, and earth/gravity. What we've done in the past is we have made interaction tables such as this. We list the components both by column and across in row. And then we put either a plus or a minus in each box, indicating whether or not the components are interacting with each other. So we put a plus in there if they're interacting with each other either by contact force or force at a distance, and we put a minus in the box if they aren't interacting with each other at all. On the right-hand side, we show a force model of the three components as well as the contact and force at distance arrows. Notice the arrows are solid for contact forces and dashed for forces at a distance. And the arrows are always in pairs with each other. So this is also for the ball before it's dropped. Now today, we're going to work on figuring out how to do a free body diagram. The model of a single object and the force that act on it is called a free body diagram because the object is freed from its surroundings. So once you see how to draw these, you're going to realize it's much easier than a force model. There's a lot fewer arrows. The influence of all the surroundings is represented through the forces they apply to the object of interest. In this case, it will be a tennis ball. This new model will show only the tennis ball and the forces it is subjected to before and after it was dropped, not the forces it applies or the other components of the system. It's a much easier model. So again, quick review. We're looking at me holding a tennis ball, so the components are the hand, the ball, earth/gravity. We know how to do an interaction table. We know how to do a force model. So our next step is to figure out how to do a free body diagram. So I have this set up here, and these are the items I will be using to draw the free body diagram. I have them already pre-made to make this a little bit faster. So again, the components are the hand, the ball, and earth/gravity. So I'm going to start out by moving the ball up here. And then what I have to do is I have to look at it and say, okay, so what forces are actually acting on the ball? Well, I have the hand adding an upwards vertical force, so it's a pull force, so that's the hand. And then I have gravity providing a vertical downward pull force as well, and that's earth/gravity. Now if you notice, the length of the arrows are equal to each other. So what that means is the item is not moving. So then I put my little no motion item up here, and this tells me that in fact the ball is not moving. And that is a free body diagram of me holding a tennis ball. So let's move on to the next part. So again, a little review. We have an interaction table in the upper right hand corner. We have the force model on the left hand side on the bottom, and we have our free body diagram on the right hand side. Notice the length of the arrow makes a difference. That indicates how much force is being applied, which we'll come back to in a few moments. And we still use a solid arrow for contact forces, and we still use the dash arrow for forces at a distance. One of the key things we want to make sure we do is label all the components, like I have them on the diagram. And we also want to include the no motion sign. All right, so this time I took a picture of the ball falling. So I've let go of the ball and it's falling as indicated by the blurry motion. So now we're going to draw a free body diagram for the ball falling. So we're going to start out with a ball and put it up here. And then we have to look at what forces are acting on the ball in this image. Well, there's no longer a hand holding it up in the air. So the only force we have really is we have a vertical pull force at a distance created by earth/gravity. As a result, the ball is moving in a downward motion. So to do that and indicate that, we put this arrow in here called a motion force arrow. And this is now telling us that the ball is in fact falling down because the only force acting on it this time is the earth/gravity pulling it down. We don't need these other items down below. So that's a free body diagram of the ball falling once it's been released. Now sometimes we have two different forces acting on an object that are not the same magnitude or strength. So that's what this is going to indicate. And our free body diagram will allow us to figure out, well, what's going on. Is the ball moving or is the ball not moving? So we have a larger force, of force 1, pushing horizontally to the right. It's a contact force, as indicated by the solid arrow. It's pushing to the right, and it's a long arrow. The other force we have is pushing to the left on the same ball, but notice the length of the arrow is much shorter. I just made this arrow thicker, so when I do the rest of this demonstration, it will make more sense. Now, the challenge we have here is we have to decide if we have a long force on the left side, a long force arrow on the left side, and a short force arrow on the right side, is this ball stationary? In other words, no motion, or is it going to move? Well, what happens is, if this force is larger than the other force, this force creates what's called a net force. So I'm going to put that over here. Now, a net force means if we take the two forces and we subtract them, we have leftover force. So I'm going to take this force and move it over here just to show you what I'm talking about. So if I put this force here in the opposite direction of our first force, all this leftover blue force, which is right here, whoops. Oh, there we go. Come on. There. Our leftover blue force is going to the right. So if I put that leftover force right here, what it tells me is that I have a contact force, a net force, to the right, which means that I have this ball moving to the right, so I have a motion arrow. So I want to put that there, and I can put this one up here too, just to verify. The no motion force symbol isn't used in this. So again, I have what's called a net force, which is this leftover force when I subtract these two forces, and then that means that the ball is moving to the right. All right, now let's try something else. Let's say I give you the diagram, and you tell me what's happening. So force 1 is pushing, contact force, solid arrow, horizontally to the right, whereas force 2 is pushing with a contact force, horizontally to the left. If you notice, they're both contact forces, opposite directions. However, one arrow is much longer than the other. So will this result in no motion, or will this result in motion? Again, if we have unbalanced forces, we create a net force in one direction, and in this case it will be to the left. Therefore, the ball will begin moving to the left because it has a net force motion to the left. All right, let's try the next one. On this one, we have force 1, force 2, both contact forces again, both horizontal forces, and they're both pushing on the same object, the ball. And if you look at it, it looks like the arrows are the same length, so they're equal and opposite in strength and magnitude. And when they're equal and opposite in strength and magnitude, what happens is the forces actually cancel each other out. So that means there is going to be no motion. If we go back to this other one, these two forces are working against each other, and when they're working against each other, we call that counteracting. It's not strong enough to cancel each other, but they work against each other in opposite directions. And again, since this one is longer than this one, we have a net force resulting in motion. Now let's try two more. So we have the ball, and we have a hand lifting it up, contact force, vertical pull motion. We have a force at a distance of the earth/gravity. This is a force at a distance, since it's not touching it directly. Notice the dashed arrow. The two arrows appear to be the same length, so we will say that they're the same length for all practical purposes. So now the challenge is this ball moving or not moving? If you guessed that the ball is not moving, or better yet, you knew that the ball was not moving, then you'd put the no motion sign there, and that is correct. In the image to the right, diagram 2, we have a longer contact force arrow by the hand acting on the ball. Then the force at a distance arrow, the dashed arrow, created by the earth/gravity in a vertical direction as well. The result is we have a net force in the upward direction, so that means that the ball is moving upwards because we have a longer force here than we have down here. And that's it. That's our free body discussion. So I hope this helps you. Thank you.